As of now, we discussed about the asynchronous counter, where the output of first stage is connected to the clock pulse of the next stage. Okay, but the problem with the asynchronous counter was the next stage will wait until there is no change in the output of the first stage. So the total time requirement is very high. Okay, so they are not synchronized. All the flip-flops are not controlled with the same clock pulse. Okay, so only one flip-flop is controlled with the clock pulse, and rest all other flip-flops are depends on the output of the previous stage or the previous flip-flops. So this unnecessary create the delay. So to overcome that problem, oh yeah, and of course there is no synchronization between the flip-flops. So to make it synchronous, the counter should be like the synchronous counter, where the flip-flops, all the flip-flops are controlled with the same clock pulse, and output of first flip-flop is connected to the next stage input. Okay, so so if I have to understand the nature of asynchronous and the synchronous flip-flop, so the asynchronous flip-flop is something like this, where I'm connecting this output to the next stage clock pulse. But if I'm talking about the synchronous one, so the output of the first stage is connected to the input of the next stage, and the clocks are common for all the flip-flops. Okay, so this is the only difference between synchronous and asynchronous. Now suppose I have to design a synchronous counter, then what kind of procedures I have to follow? Okay, so here are some procedures. Like first I have to find how many number of flip-flops are needed, so that completely depends on what is the mode of requirement. Then I have to design the state diagram based on the states, and then I have to come up with the excitation table based on the past and present inputs, and then minimize the expression based on the like this. I have to solve that K-map, and then design the circuit diagram. So these all are the procedure that I have to follow. Yeah, of course, the same procedure we followed for the asynchronous designing as well. Okay, but let us try to see how we can design the synchronous counter with the help of this procedure. Okay, so the only difference between the synchronous and the asynchronous counter is like the connection connection of the clock pulse and the inputs. Okay, in the asynchronous one, the clock pulse depends on the clock pulse for the previous next state depends on the previous state output, whereas for the synchronous one, the clock pulse are common for all the flip-flops. Okay, so this is the basic difference between these two. Now we know the procedure, what procedure I have to follow. So let us try to follow this procedure and try to design some synchronous counter. Okay, so how we can design the synchronous counter? Suppose I have to design the mode 4 synchronous up counter, then what I have to do? Mode 4 asynchronous counter means what? Here m is equal to 4. Okay, m is equal to 4. What it means? 2 to the power n. If I try to find the value of number of flip-flop, so the n is coming around 2. So 2 number of flip-flops are required to design this counter. Okay, now next one is, this is the sequence it is going to follow: 0 to 1, 1 to 2, 2 to 3, and then 3 to 1. So this is the sequence which the up counter is going to follow, because we are designing the up counter. Okay, so this is what the sequence is. Now the next stage is very important. Okay, I have to write all the clock pulses, and then present state in the next state, and then accordingly I have to find the excitation table. Yes, I have written here TA1, TA2, what TA0. What it means, I want to design this counter with the help of T flip-flop. I can also use the JK flip-flop. Okay, so JK flip-flop or the T flip-flop is possible. Both can be used to design any of the counter. But T flip-flop is preferable because it has only one input, so the less number of K map need to be solved. Okay, otherwise for the JK flip-flop you need double calculation. Okay, but if it is not given like which flip-flop you have to use, I will recommend to use the flip-flop. But if it is mentioned like you have to use JK, then definitely you have to use that one. Okay, so let us try to fill this table based on the state diagram. Okay, how it will look like. So total number of pulses are, because it is the up counter, so it will start from 0, then 1, then 2, and then 3. So these all are the clock pulses. Now the present state is like, if I try to write in the binary, so it will be 0 0 0 1 1 0 and 1 1. So these all are the sequences. Next stage is like, if the present state is 0 0, if the present state is 0 0, next state should be 1 0 1. So the next state is 0 1. If the present state is 0 1, so the next state is 1 0. If present state is 1 0, next state is 1 1. And if present state is 1 1, then next state should be 0 0. So the next state will look like this one. Okay, so based on the present in this one, so we got this particular thing. Now we know the excitation table of the T flip-flop. Okay, what this T flip-flop says? T flip-flop says that the Q T plus 1 is nothing but this is QT and XORing with the T. Okay, so this is the characteristic equation of the T flip-flop, which we already know. Okay, so if I am using this one, so the what will be the TA1 and the TA0, TA1 and TA0, that will based on this equation or the excitation table. Yeah, we also know that QT and the QT plus 1 and the T. So the excitation table for T flip-flop is like 0 0 0 1 1 0 1 1. So if it is like that, the excitation table said like 0 1 1 0. This should be the excitation table. So this is the excitation table for the T flip-flop. So let us try to see here. If I want to make for the A1, so what I need to consider, A1 from the present state and A1 from the next state. So the QT, this will treat as a QT. Yeah, this is nothing but this is for QT and this is for QT plus 1. And based on that, I will calculate the T for A1 and A2. Okay, so let us try to see what it will be. 0 and 0. So 0 and 0, T should be 0. 0 and 1, 0 and 1, T should be 1. Okay, 1 and 1, T should be 0. And 1 and 0, it should be 1. So 1 0 1 0 1 0 1 is the TA1. Similarly, I have to calculate for TA0. For in that case, what I have to use? I have to use this one. So 0 and 1, 0 and 1, that gives 1. 1 and 0, that gives 1. 0 and 1, 1, and 1 and 0, 1. So this all will be 1 1. So this is how we got the complete truth table for this one. Okay, so based on this excitation table, we can come up with like what is the value of this excitation. Okay, so the excitation table is required. Okay, once we are ready with this one, the next stage that I have to follow is the KMF for TA0 and TA1. Okay, what is the KMF for TA0 and TA1? Let us try to see here. If I have to make the KMF for TA1, the TA1 KMF is like 0 1 0 1. So it will be 0 1 0 1. Okay, similarly the KMF for TA0 is 1 1 1 1. Okay, 1 1 1 1. What does it means? It means that this is the pairing which is possible. So TA1 is nothing but, so TA1 is nothing but it is the A0. Okay, and TA0 is nothing but this is the logic 1. Okay, because this whole quad is possible here, so that will give you the 1. So TA0 is 1 and TA1 is A0. Okay, once we are ready with this one, what I have to do, I have a 2 flip-flop where the input of first flip-flop will be connected to the 1 and input of the second flip-flop TA1, that will be the output of the first flip-flop, where A0 is the output of the first flip-flop, right? So this is how the circuit will look like. A0 is nothing but this is the input for this is the TA1. So TA1 is same as the A0, and TA0 is nothing but this is logic high, and the clock will be connected for all the flip-flops. So this is how the simple circuit for the flip-flop or for this mode 4 up counter will look like. Okay, so this is how the mode 4 up counter can be designed. And similarly, this is the truth table, because both the flip-flops will be controlled at the same time. So once there is a rising pulse, like initially, let us assume it is the 0 0. So it is the initially it was 0 0. So after first clock pulse, this will become 0, and because A0 initially A0 was 0, so 0, and even though there is clock pulse, it will maintain the same logic, and so on. So the waveform will look like this one. So this is how the timing diagram for the asynchronous up counter will look like. Okay. So this is how we can design the counter. So this is really very important, especially if we want to understand how we can design the counters. Okay. Similarly, if I have a mode 8 counter, so the present states will be A2, A1, A0. Next state will be A2, A1, A0, and then we need 3 flip-flop TA2, TA1, and TA0, and accordingly we have to solve it. We need 3 K maps and 3 flip-flops, and then we have to connect all the terminals accordingly, whatever the output is coming. Okay, so based on that we can do that. So this is doable. Okay. Next one is, here we have some tutorial questions, if you have any doubt on this, then you can ask the questions, right? So this is important. How we can design the counter, you should ask the question. If you do not have any doubt, we can move ahead. So here are some tutorial questions that you have to design mode 3 up synchronous counter using JK flip-flop, synchronous mode 5 counter using T flip-flop, BCD up counter using JK and the T flip-flop. Okay, so this is how you can do it. Okay, now so these are some questions. Let us take some examples, some more examples, right, so that you will be able to understand how exactly we can design the counters. Okay, so the counter designing is really very important. Let me go back to the previous slide. Suppose I have to make the mode 3 counter. Okay, if I have to make mode 3 counter, let us assume with the help of J. Okay, so how it could be done? Let us go back to the previous slide. If I have to make mode 3 counter, the sequence will be 0, 1, and 2. Okay, 0 to 1, 1 to 2, and 2 to 3. And this is invalid state. Okay, so if the present state is 0, like this one, 1, 0, the next state should not be 1, 1. This should be 0 and 0. Okay, so this is how the truth table will be. Okay, so and if the present state is 1, 1, then the next state should be don't care, it does not matter. So it will become 0, 0 here and don't care here, and then accordingly just solve it, and you will get the TA1 and TA0, and you can get it. Okay, so this is how the mode 3 can be designed. Okay, so this is the simple way. Similar approach will be applied. Okay, now let us try to design some different kind of counters. So here I have to design modulo 8 gray code up counter, which is a synchronous one. Okay, so I have to design a synchronous one. Synchronous means I have to connect all the clock pulse at the same signal. Okay, and the modulus 8 means like mod 8 0 to 7, that should count from 0 to 7. And then gray code up converter means like it is not normal. Like if I'm talking about a binary counter, in that case it will start from 0, then 1, then 2, 3, 4, 5, 6, and 7. So this is possible in the simply binary counter. But if I have to make the gray code counter, then how it is possible? Let us try to understand this one, because the gray code is something different from the binary one. Okay, so suppose I have a decimal digits which is from 0 to 7. So to make it modulus 8, okay, modulo 8, okay, so mod 8 counter is possible from 0 to 7. If the sequence is from 0 to 7, what it means, this is a mod 8 counter. The binary equivalent of this, all the decimals are 000 to 111. Okay, but if I want to make the gray code of all these things, what the gray code will look like? Okay, the gray code will be like for 000 it will be 000. Okay, for 001 again, like for 1 it will be 001, but for 010 it will be 011. Okay, then 010, and then 110, 111, 101, and 100. So this is the gray code of the binary equivalent. Okay, so let us try to fill this up. Okay, if the clock pulse is something like this, 0, 1, 2, 3, 4, 5, 6. Okay, so what should be the sequence? If we try to see here, this is nothing but this is same as 0. So the min term will be 0, M0. Okay, if you see here, this 001, this is nothing but this is same as which is the min term 1. 011, this is different. This is not like M2. This is like M3. Okay, this is like M3 in the binary, because the any of the circuit will not understand whether it is like whether it is binary or gray. They will simply understand 0 and 1 only. Okay, so I have to consider it like the sequence should be 0, 1, 3, and then 3 is equivalent to M2. 4 is nothing but this is like 6, M6. 5 is nothing but this is like M7. Okay, and the next one is this one 6, which is 101. This is equal to like M5, and then M4. Okay, what does it means? It means that the sequence which it is going to follow is from 0 to 1 to 3 to 2, then 6, then 7, then 5, then 4, and then it is coming to 0. So this is the sequence which this counter should follow. Okay, so if it is following like this sequence 0, 1, 3, 2, 6, 4, 5, 7, then this is nothing but this will act as a gray code. Okay, so this is the sequence that this has to follow. Okay, now let us try to fill the tables based on this one. Okay, if it is M0, so the present state will be like 0, 0, 0, M1, 0, 0, 1, M3 means 0, 1, 1, okay, 0, 1, 1, and then 0, 1, 0, M6 means like 1, 1, 0, okay, 1, 1, 1, 1, 0, 1, and 1, 0, 0. So this is what exactly what I have just followed what the min term says. Okay, because these are the present state. Okay, and accordingly we have just made it. Now what will be the next state? Okay, the next state is something like this one. If the present state is 0, 0, the next state should be 1, right? So the next state, let me change the color so that will help. Okay, so the next state is 0, 0, 1. Okay, if the present state is 0, 0, 1, the next state is this one. Okay, so 0, 1, 1, 0, 1, 0. Okay, 0 1 0, then 1 1 0, 1 1 1. Okay. And then 1 0 1 1 0 0, and once it reaches to 1 0 0, it should come back to 0 0 0. So this is the truth table that is important. Okay, so if anyone has any doubt at this stage, you can ask the question, because this is really very important that you should understand. If anyone has any doubt how I got to know like what is the next state, yeah, simply just present state, then next, then next, then next, and this is how we can come up with this one. Now let us talk about what is the excitation table. Okay, so the excitation table, we know that it looks like qt and the qt plus 1 and the t will be something like this: 0 0 0 1 1 0 and 1 1. If this is the sequence, then the t should be 0 1 1 0. So this is what we know, what is the excitation table for the t flip flop. Considering this one, if I have to make for t2, so I will use a2 a2. Okay, a2 and a2. So for the present and the past, so here 0 and 0, 0 and 0, that will give t that is equivalent to 0. 0 0 0, 0 and 0 0, 0 and 1, 0 and 1, that will give you the 1. Then 1 1 1 1 is 0, 1 and 1 0, 1 1 0, and 1 0 is 1. Okay, so this is how I can make the table for t2. Okay, t2 is fine. Now let us try to see what is the table for t1 and t0. Okay, so can anyone tell me what is the table for t1 and t0? What is the table for? Yeah, based on this one, just use this excitation table and try to fill the values for t1 and t0. I am giving some time to think about this one, and then please come to. Okay, no one is ready to respond. Fine, as expected. Okay.
Sir, T.
Yeah.
Sir, M0 will be 0 for T1.
Okay, 0.
Then 1. Then 0. 0. 0. 1. 0.
Yes.
And 0.
Okay, absolutely correct. Similarly, we can make for the t0.
Yes.
So similarly, we can just we have to use this excitation table. So it will come like 1 0, then 1 0, then 1 0 1 and 0. Okay, so if you see like a0 for both, the t0 is coming like 1 0 1 0 1 0 1 0. Okay, once we are ready with all these things, so let us try to see what are the minterms which are available. So for t2, the minterms are 2 and the 4 minterms like M4 and M2 are available. Okay, so for T2 it will be the 2 and 4. For T1 it is 1 and the 7, 1 and 7, and for T0 we have 0, 3, 5 and 6. Okay, so these all are the minterms which are present here. Once we are ready with all these things, the next step is just to simplify the K-map for T2, T1 and T0. So the simplification of K-map is required. Okay, how to simplify it? Let us try to see. We know that T2, T1 and T0. Now the for T2, how it could be done? So 2 and 4 will be there. So for 2 and 4, 2 and 4 is 1. Okay, 2 and 4 is 1. Okay, and what about T1? For T1, 1 and 7 is there, 1 and 7, and for T0, 0, 3, 6 and 5. Okay, 0, 3, 5 and 6 are there. Now let us try to simplify it, how the expression will look like. If you try to see here, this one, how this looks like, because it is not possible to make the pair of this one. Okay, so this looks like, if you try to see this, T2 is nothing but it is A2, A1 bar, A0 bar, plus from here I will get A2 bar, A1, A0 bar. Okay, so if you see here, A0 bar is common in both. Okay, A0 bar is common in both. So if I can take the A0 bar common, so I will get something like A2 A1 bar plus A2 bar A1, and then that it, yeah, let me write it, A2 A1 bar plus A2 bar A1, and this is nothing but this is the XORing of A2 and A1. Okay, so what I can write, I can simply write A0 bar into A2 XOR A1. So this is the expression. Now let us try to solve for T2. What is the T2? Okay, T2 is like, see here, I have to simplify. Yeah, just like that, I have to simplify it, right? So if you see here, this one will give you like A2 bar, A1 bar, A0 plus A2, A1, A0. Okay, here I can make the common like A0 is common again, and here I can see this part and this part is there, and this is nothing but this is the XNOR. Okay, A2 bar A1 bar plus A2 A1, what it means, this is nothing but this is the XNOR. So I'm directly writing here A0 into A2 XNOR of A1. Okay, so this is possible. Third thing that third one, like T0, sorry, not, this is not T2, this is T1, right? So the T0 is equal to, yeah, so directly if you can see here, this looks like a diagonal. Okay, so if they are diagonal, in that case I can say they are, and direction of diagonal is in this direction, so they are nothing but they are the XNOR kind of a structure. Okay, they are something like a XNOR kind of a structure. Oh, sorry. Okay, And if they are XNOR structure, XNOR of nothing, but this is the A2 XNOR A1 XNOR A0. This is what we have already done it, right? So this is how the circuit will look like. The first thing, TA0, this is nothing but the XNORing of this one. So TA0, TA1 and TA2, based on whatever the expression it is, just I have to simplify it and I will get the answers. Okay. So this is how we can make the circuit based on the truth, based on the requirement, whatever I have.